Hi everyone, and in today's video we are going to see an alternative way to calculate residue that doesn't involve the Laurent expansion. So we start with considering a function f of z, and we say that this function has a pole of order m at point z equals to z0. So this is the function that we are considering, and we are saying that it has a pole of order m at a point, that is a point in the complex plane, that is denoted with z equals to z0. That means this is the point where it has a pole of order m. So the Laurent series about this point has the following form. So the Laurent series for this f of z will look something like this around z0. So let me write it down. And you see that I have give this dotted because you know that there are many terms. So let's just give some dots about it. And this a minus 1, that means this coefficient, this is the residue, and this is the thing that we're interested in getting. So we'll see how to extract that in a few bit. So, and after this residue part, this is just the analytical part, or so to say the Taylor expansion part. So this is the Laurent expansion, or so to say the Laurent series. So now what we're going to do is that we're going to find an alternative way to calculate this guy over here. So we want to get this coefficient only, this a minus 1, or as you already know that it's called the residue. So the first thing we're going to do, we're going to label it as equation 1, and then we're going to multiply both sides of 1 with z minus z naught to the power m. That means the next line will look something like this: z minus z naught to the power m, and this should give us a minus m plus a minus m plus 1. Obviously these are subscripts, and this will be z minus z naught dot 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 plus a minus 1. And you can see that since there was a z minus z naught over here that was in the denominator, and we're multiplying with z minus z naught to the power m, this will simply yield z minus z naught to the power m minus 1, and then you have the Taylor expansion part. I'm not going to write it down explicitly, I'm just giving some dot dots. And since we will only want to extract out this part over here, that is a minus 1, or so to say a underscore minus 1, that is the residue, we are going to differentiate both sides with m minus 1 time with respect to z. That is, if you call this expression 2, so now we're going to differentiate 2 with respect to z. Let me just, so this WRT means with respect to z, m minus 1 times. Why m minus 1 times? Because if I do this differentiation m minus 1 times, all the terms on this side, that means this term, this term, this term, and all these terms will go away, and only this part will remain, and this analytical part will remain. So that's why I want to differentiate m minus 1 times. So if you do that, it will look something like this: ddd of m minus 1, and it says, because since we're differentiating, we have to differentiate both sides, and the left hand side will look something like this. And this should give us a minus 1 times m minus 1 factorial, because this is pretty basic thing, because if you have x to the power n and if you differentiate it with respect to x n times, because let's say you have x to the power n and you want to, sorry, it shouldn't be x, it should be rather n. If you differentiate this x to the power n times, this just gives you n factorial. This is some basic calculus that you already know. So we found out this part. However, there is this analytical part, and this analytical part, since this is a Taylor expansion, can be written as follows: as a summation. Obviously you can leave it as a dot dot dot, but I'm just going to use this summation symbol to indicate all the terms that is appearing over here that I didn't write explicitly. And this will look like this: Bn, where b's are some coefficients, and it will look like z minus z naught to the power n, and this is the summation. So we are almost there. We want to extract out only a minus 1, that is the residue. So now let's divide both sides by m minus 1 factorial. So this will look like m minus 1 factorial. It looks bad. It's 1 factorial. There is this derivative operation. And the rest of the things you put them. This was just a minus 1, that is the residue, and there you have a m minus 1 factorial over here, because you're dividing it, the whole expression, with m minus 1 factorial, and there is this summation part, z minus z0 to the power n. Now you can see that now if someone takes the limit z goes to z naught, all the terms over here, so let me just indicate it, all the terms over here will cancel out and they will go to 0, because it has the z minus z naught to the power n, where n is equals, where n starts from 1 and goes up to infinity. And so that's why we want to take both, we want to take limits on both sides. So now finally take the limit. So this will look like limit z goes to z naught. Obviously you can put this factorial inside this expression, it doesn't matter because it's a constant, and you have this m minus 1 factorial, and you have d to the power m minus 1, d of z m minus 1, your f of z, z minus z naught to the power m equals to, since this is a constant, the limit won't have any effect on it because there is no z over here. And if you okay, let me just go a bit downward because this expression is pretty big. So this part on the right hand side will have limit z goes to z naught 1 by m minus 1 factorial. Okay, this is pretty big, so sorry for that. I need another line. I need another line for this. So this guy over here, this will be equals to a minus 1 plus limit z goes to z naught. You have 1 divided by m minus 1 factorial over here, and you will have sum over this n equals to 1 to infinity bn z minus z naught to the power n. And if you put the limit, because limit is a linear operator, it will go inside the sum, and after you evaluate this limit over here, all these terms will cancel out and they will go to 0. So finally we will have a minus 1, or so to say the residue, is equals to limit of z goes to z naught. There will be this m minus 1 factorial, d of m minus 1, dz of m minus 1. Then you will have your f of z, and you should have this z minus z naught to the power m. Z minus z naught to the power m. So this is the formula that allows you to calculate residues without explicitly using the Laurent expansion. And let's now try to see an example to finish the video. So the example we are going to consider is something like this. You have a function f of z, which is written as e to the power iz divided by z square plus 1 whole square. So the technique to find the poles or singularities you already know is that we need to check when the denominator goes to 0. And the denominator goes to 0. If that's the case, we can easily see that this z square plus 1 should be equals to 0, and that gives us z is equals to plus minus 1, right? So let's write that down first. So if you just put z plus I, one of the roots, and obviously you use this square thing as well, and one of them is z minus I, you can write it like this. And finally you can write it like z plus I squared, z minus I squared, right? Now we want to find the residue, or we ask the question, what is residue at point I? So residue, let's write it as RES to shorten our notation. This RES will mean residue, and the bracket is saying that it's I. That means at the point I, that means this is coming from z minus I. So you notice that these are double poles at z equals to plus I and z equals to minus I. So these are double poles. And if you recall our formula, that is this one over here, this m was the order of the pole, right? And you can see that for calculating the residue at z0, that is for a specific point, you had to take the function, then you have to multiply the function with z minus z0 to the power m, again where m is the order of the pole, and finally you need to do some derivative thing, and after that you need to evaluate the limit. So let's see how this works. It's not as complicated as it seems. So what we're going to do, that we're going to calculate residue for the point I, that is corresponding to z minus I. So here our function is this guy, right? This was our function f of z. So first evaluate f of z times z minus I squared. Why? Because the value of m is 2. It's a order 2 thing, or a double pole, whatever you want to call it. And if you do that, and if you put the expression, that is this expression over here, if you put this expression, you can see that the denominator z minus I whole square will get cancelled out with this. So this will just be e to the power I z, z plus I whole square, right? Now our m was 2. So since m was 2, if you see this formula, if you put the value m equals to 2, that means there is one derivative only. That means dd of z, right? So now we need to differentiate this thing one time, because the value of m is 2. So we have to do, this is the next step. Obviously you can do it just plugging all the things in the formula, but it might get messy sometimes, so I'm just breaking it down. And after you get some practice, you can just easily do it even without some calculation at all. So we have to find the derivative of this guy over here. So this is e to the power I z, z plus I squared. Okay, if you use the product rule or the quotient rule, whatever you want, I'm gonna go with the product rule, and that's easier because there is no ambiguity in the sign. So that is whether it's the plus or minus or yada 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 that you see in your differential calculus course. So if you just use the product rule, the derivative will be something like this. And now, since we are done calculating the derivative, let's call it 3, and you can see that we have done all the works over here except for calculating the factorial and taking the limit. So now since m equals to 2, that means 2 minus 1 factorial is just 1 factorial, that is just 1. So we are also done with calculating the factorial. Now finally we want to take the limit. So finally taking the limit, and here the limit z will go to I, because that's the point we are interested in calculating the residue, because we are calculating the residue for I. So if you recall, this formula was valid for when z goes to z0. That means you are interested in the residue at the point z equals to z0. So since here we are interested in calculating the residue for the point I, that's why we have to take the limit z goes to I. And obviously there is this 1 that is coming from this 1 divided by m minus 1 factorial where m equals to 2, but since this is just 1, we don't need to write that. And we need to take the limit of 3, because that's the differentiation we did to complete this part first. So let's take the limit. So this is just, again, let me write down the whole thing. And you can easily find out the limit because there is no ambiguity over here, no 0 by 0 or no infinity by infinity formation. So if you just plug in the limit, you will have on the denominator, this will be 2i squared. Here you'll have, oh yes, I think I made a mistake. Sorry about that. When you differentiate it with respect to z, here you'll have a I on this term, because first you are differentiating e to the power iz with respect to z, so the I will come down, and secondly you are differentiating z plus I whole square, and that's why there is this minus sign, and there is this z cube and all that. So yeah, there will be I over here. So this is I, and after evaluating the limit, this will be e to the power I squared, because I times I, minus 2 e to the power I squared, and you will have a 2i whole cube over here. Now at this point you are in principle done, but let's try to simplify the results a little bit. If you simplify the results, it will look something like minus I e to the power minus 1, and in the denominator you will have a 4, and here you will have a plus 8i 2 e to the power minus 1. And if you simplify it a bit further, obviously e to the power minus 1 means 1 upon e, so I can factor that out, and I'm left with I by 4. And since there is I in the denominator, what you can do is that you can write minus I whole square, and you can cancel one of the i's, and you will have a minus I. So ultimately you will have something like minus I by 4 over here as well, because this 2 and 8 will give you just a 1 upon 4 factor, and this minus and this plus will eventually result in a minus sign. So finally you can have minus 2i 4e, that is just minus I by 2e, and this is the residue at point z equals to I. Similarly, you can calculate the residue for the other point, that is z is equals to minus I, but there you have to take the limit z goes to minus I, and obviously you need to multiply z plus I whole square with the function itself, because that's the point you are considering, right? So this is how you can calculate residues, and this will be particularly helpful when we'll see some application of residues in evaluating contour integrals that will actually involve some improper integrals, because expanding some function always in a Lorentz series is not convenient. So that's why this brute force method is sometimes really helpful. So this will be it for today, and I'll see you guys in the next lecture. Thank you.